So in the first part of this video lecture, we have talked about the sigma algebra generated by any class of subsets of a given sample space. And now we're going to talk about a particular case, which will be the most important one, which is the Borel sets of real numbers. So we have seen the notion of this sigma algebra generated by an arbitrary class of subsets of a sample space. And it was defined as it is a sigma algebra itself, it contains the class, and any other sigma algebra that contains the class must contain it. And we have seen a very useful property that will be useful exactly in this second part of the video lecture, which is in order to check that the sigma algebra generated by a class is contained in the sigma algebra generated by another class, it is enough to check that the first class of subsets of the sample space is contained in the sigma algebra generated by the second class. We are now ready to introduce Borel sets on the real line. And here's the definition. If the sample space is the real line, then the Borel sigma algebra, denoted by B of R, is the sigma algebra generated by open sets. Okay? It is also the smallest sigma algebra that contains all the open intervals or all the closed intervals. So it's also the sigma algebra generated by the family of open intervals or the family of closed intervals. Now remember the extended real line, which is the real line where we add 2 points that we call plus infinity and minus infinity. And for that set, we define the Borel sigma algebra on that set as the family of subsets which are given by a Borel set on the real line, maybe adding points plus or minus infinity to it. So these are exactly the sets that when we intersect with the real line, meaning we take away plus or minus infinity in case they have it, this becomes a Borel set on the real line. And sometimes we will denote these sigma algebras simply by B when it is very clear from the context that the sample space is R. Then B means simply B of R. And when it's clear that the sample space is R bar, the set of extended real numbers, then we just write B, knowing that it denotes B of R bar. There are many different ways to generate the class of Borel sets B of R. Here I'm listing only a few of them, just 6 different ways to generate the family of Borel sets of the real line. And it is the following. We consider these 6 classes of subsets of R. First, closed subsets of R. Second, open subsets of R. Second, the class of intervals of this form. Open intervals where A and B are allowed to take values infinity. So these will be open intervals which may be infinite or not. Or the family of finite intervals, so A and B are both finite numbers, finite intervals of the form open A, B, closed, so intervals that start at A, end at B, and are open on the left and closed on the right. What the family is, just the family of semi-infinite intervals which are closed on the right. So they are semi-infinite on the left and closed on the right, and they end at some point B, where B must be a finite real number. Or the family of semi-infinite intervals of the form minus infinity B, open at B, for B being any real number, finite real number. There are more examples. These 6 are enough to illustrate there are many different ways to generate the sigma algebra of Borel sets. So here's the proposition. The proposition says that the sigma algebra of Borel sets, which by definition equals the second one here, it is the sigma algebra generated by open subsets. Well, these are actually all the same. All these classes, they generate the same sigma algebra, and this is exactly the Borel sigma algebra. So I'll let you struggle with the proof, and write down a formal proof by yourselves. I'll give you a good hint of how this proof goes. So the proof, it will go as follows. We want to show that these 6 generated sigma algebras, they coincide. And how are we going to do that? We're going to show that the sigma algebra generated by the second class out of those 6 listed before. Let me go back. Here we are listing 6 different classes of sets, and we are considering the sigma algebra generated by each one of them. So we're going to show that the sigma algebra generated by the second class is contained in the sigma algebra generated by the sets in the first class. Then we show that the sigma algebra of the sets, the sigma algebra generated by the first class, is contained in the sigma algebra generated by the second class, which already means that these two are equal because this one appears again here. Then we show that sigma of E2 is contained in sigma of E3. Then we show that sigma of E3 is contained in sigma of E4. Then we show that this is contained in sigma of E5. Then we show that it's contained in sigma of E6. And then we show that this is contained in sigma of E2. And since we close the loop here, because this is E2 here again, this means these are all the same. So this is how the proof goes. So we have all these inclusions to prove, and I will prove one of them here. There's another one that is proved in the lecture notes, and the other ones will remain as exercises for you. The proof uses this proposition from the previous video very strongly. So now we're going to see how this proposition appears. So we're going to prove this one here, that the sigma algebra generated by this family is contained in the sigma algebra generated by this family. So let's start the proof. Take some set, any set, and this the second family. So what is the second family? This is an open set. So this A here is just an open set. A is an open set. Now we know from metric spaces, and if we don't, it's okay, we just have to believe it, that on the real line, here we are on the real line, open sets, that's a theorem, they can be written as the countable union of disjoint open intervals. Okay? So this A is an open set. Why is it an open set? Because it's a member of E2, and E2 is exactly the family of subsets of R which are open. So being an open set, it can be written as a disjoint union of intervals, open intervals. And being open intervals, what does it mean to be open intervals? It means exactly that they belong to E3. E3 is the class of open intervals. And E3 is, of course, a subset of sigma of E3. So all these little intervals, they are in sigma of E3. But then A is the union of these intervals. And sigma of E3, it is a sigma algebra. So since all these sets, each one of them is in sigma of E3, which is a sigma algebra, then their union is also in sigma of E3. Because sigma algebras are closed under countable union. Since all these are in sigma of E3, their union is also in sigma of E3. But wait, that means A is also in sigma of E3, because A is exactly the union of these intervals. And what is A? Oh, A was chosen as an arbitrary set of this class. We didn't make any assumptions about A besides the fact that A belongs to this family. So E2 is actually a subset of sigma of E3. Yeah? And we have proved this by taking any element of E2, going through some argument to conclude that it must be in sigma of E3. So we just concluded that E2 is contained in sigma of E3. So by the previous proposition, which one? This one here. By this proposition, we can conclude that in fact sigma of E2 is contained in sigma of E3, which is exactly what we are trying to prove.